Hi, my name is Berkay and here I am with another video. In this video, I will going to show you how to design an FIR 180 tab bandpass filter with using VHDL. But first, I need to show you what is a FIR filter and how does it work. And as you can see, this is an FIR filter. Now, there is some time delay operators in here, some filter coefficients, and some arithmetic operators. And this is it. This is an FIR filter. And now I will going to explain you how it works. We have an input data and 32-bit single precision data. And that data will be multiplied by the very first filter coefficient. And it will going to add itself with the rest of the filter. But all the other tabs are empty right now, so it will just going to edit with bunch of zeros, and this will be our very first data out. Then that data will be shifted towards the time and will be multiplied by the second filter coefficient. Then a new data will come in and it will going to multiply it by the first filter coefficient. They will be added together and this will be our second data out. Now we were going to do that until all the data is processed. But as you can see, this is a 3-tab FIR filter. But we were going to design an 180-tab filter because we want a better data out signal. Now let's start, but first we need to generate our signal and noise. So we will go to the MATLAB. Okay, let's start. First thing you see is my sampling frequency in here. After that, I have created my first frequency for my first sound wave and second frequency for my second sound wave. After that, I have created my time vector in here. And after that, I have created my signal by simply just adding my first sound wave to my another sound wave. And after that, I have just created some random noise for my signal and I have added them together to obtain my noisy signal. And after that, I just plotted them together and let's see. Now, as you can see, blue one is original and orange one is the noisy signal. And I will going to use that noisy signal to see if my FIR bandpass filter is working correctly or not. And but to do that, first I need to print data of this signal, noisy signal, to a txt file. But to do that, first I need to take single of it because every data in this noisy signal is double. So first I need to take single of it, and after that I need to change those numbers to hexadecimal values. So I use number to hex function. And after that I use write magnetic function and set delimiter as tab. And this function we're going to write all of our data to a txt file. And now we were going to design our filter. Now we were going to design our filter, and I know I can design my filter in MATLAB, but I just wanted to show you there are other places to design your filter. And this website is a very good example of it because you can see your frequency response of your filter and impulse response. And other math is down here. If you want, you can check this out. Now I have created my bandpass filter in here, and this is all the coefficients I need. But I need to go to MATLAB because I will going to change these numbers to 32-bit floating points. Now I have my filters coefficients in here, and as you can see they are in double format. First I will going to use single function to change them to single and use to num to hex function to change those numbers to hexadecimal values. And after that I will going to use all of these values in my VHDL code. Now this is FIR 180 bandpass filter VHDL code, and first thing we are going to check is its libraries. Now we are going to use IEEE STD Logic 1164, and we were going to use library work because we have a package in this code, so we need to use work library. We will going to use work.fpupack.org, and we were going to use work.compack.org. Now I will going to explain them in a minute, but wait a little bit. Now in this section we have entity of our code and its clock frequency, and in the port side we have clock, data in input, data valid input, data out output, and data ready output. Then in the architecture side we see a component named APU. So I need to explain this to you. APU is floating point unit core, and it's written by Ciden Eryani. It is basically an arithmetic operator for floating points, 32-bit floating points. And as you can see, in its port section, we have a clock input and input operands A and B. And in here we have APU operations, APU operation input port, and in this port you can select what is going to happen with this APU. If you give it 000, it will going to do add operation. If you give it 010, it will going to do multiplication operation. You can do subtraction, divide, and you can take square root of your floating points, but we will just going to use addition and multiplication for our project. And after that I have created a array for my filter coefficients, and I have assigned all of my filter coefficients in this array. Then I have created some signals. Then I have created my states in here, and as you can see we have an either state, multiplication state, addition state, and a result state. Then I have created a sum signal and a multi-signal. Then I have created another array for my delayed input because I need to shift my input towards the time. Now I have created a delayed input type, and I have assigned all of its values as 0. Then I have created a multiplication array, and I will going to assign every multiplication results to this array. Then I have instantiated my APU in here, and after that I have created my first process, and it's a delay process, and it will going to wait until data rate has changed because APU operator takes a lot of time to finish its operation. So you can't just delay your data for each clock cycle. You need to wait. So it will going to wait until the rising edge of our data varied input, and after that it will going to shift everything towards a delayed input array. Then this is my main process, and in this main process we will going to check if it's a rising edge of clock. Then this is where my states are defined. In the either state, it will going to give data read output as 0, and it will going to check if data read input is equal to 1 or not. And if it is equal to 1, then it will going to start the process, and it will give the start input as 1. Then it will going to change the APU operation to 0 1 0, which is multiplication operator. So we will go to the move state. In the move state, it will going to set start input as 0. Then it will give data ready output as 0. Then after that it will going to check if ready output is equal to 0 or not, and it is 0 right now. So it will going to give the first value of the rate input array and the first value of our filter coefficient. Then it will going to wait until the ready output is equal to 1. And if it is equal to 1, it will go to the result state. And in the result state, it will going to check if this is a multiplication operation or addition operation. And it is right now a multiplication operation, so it will going to come here and check if multiplication counter is equal to 180 or not. And it is not equal to 180. We are in the first state right now, and it will going to assign that results to first place of modes array. Then it will going to increase the multiplication counter by 1, and it will going to do that again and again and again until multiplication counter is equal to 180. After that, it will going to assign the last results to end of our array, and after that it will going to reset the mode counter to 0. Then after that it will give start input as a 1, and it will going to change the APU operation to 0 0 0, which means addition. Then we will go to the add state, and add state is not that different from move state. We first thing is going to do is start input will be 0. Then it will going to check if ready output is equal to 0 or not. If it is equal to 0, then it will just going to give first value of mood state and some signal. Then it will going to wait until the output is equal to 1. Then it will go to the result state, and this is caused a problem. So I have added another output assignment in the result states. Now in the result states, it will going to check if add counter is equal to 180. It is not equal to that, so it will go to this section. Add counter will be increased by 1, and then output, the results will be assigned to sum, and we will going to do that again and again and again until all the values in modes array is added together. Then it will be our data out signal. Then we will going to give data ready output as 1, and we will going to reset our sum signal to 0. Then we will go to the idle state, and we will wait for another valid data. Now this is all the code for my FIR 180 tab bandpass filter. Now I will going to show you the test bench, and in the test bench again we will going to first look at our libraries. We were going to use IEEE STD Logic 1164, and we were going to use STD Text IO and IEEE STD Logic Text IO because we need to use a text file for our input, and we were going to write our outputs to another text file, so we need to use those libraries. And this is just plain test bench tab, and after that I have created an file input file text open. Read mode is noisy signal hex.txt, and after that this is just my crack stimulus, and in the data stimulus I have created a file output file text open. It's write mode, and this is just the data path of my filtered signal txt file. And after that I have created a variable for write buff and a variable for read from input text file. And after that I have created a variable hex because it's a hexadecimal value. And after that while night end file input file loop, and this will going to take a loop until the end of my input file. Then it will going to read a line, and we're going to use hash read because it's a hexadecimal number. Then it will going to wait until the firing edge of the clock. Then it will give data in input as hexadecimal value, and it will give data valid input as 1. Then it will going to wait for 10 nanoseconds, and it will going to set data valid input as 0. Then we will going to wait until the rising edge of the data read output, and then we will going to use hash write to write an hexadecimal number to text file. Then we will going to do that until the end of the file, and file will be closed. Now I need to show you the simulation. Now first of all, let's run our simulation in 10 nanoseconds, and let's see. As you can see, data in is 0 in here, and let's do it again. Okay, and this is the first data of our noisy signal, and you can also check that in here. And as you can see, this is the first data of our noisy signal, and what's happening in here right now is basically we are in a multiplication state, and we were going to multiply this one with, let's see, we were going to multiply this one with our very first filter coefficient. Then when this is done, it will going to take a lot of time, and it's still not in here, as you can see. When it is done, we will going to multiply the other derived inputs, which is 0 right now, with every other filter coefficient, and it will going to take so much time. So I will going to just take this, and as you can see right now, it took almost 50 microseconds to done to finish just one just one data, and it will just going to take a lot of time because it's a sequential design, so everything is happening one by one. So I was just going to run this. So but before that, I want you to show this, and as you can see, we have write our first data in our filter signal txt file. Then we were going to write every other one, so let's run our filter. Now as you can see, filter is working correctly, and we are just writing everything in here, but it was just going to take so much time. Now let's see again. You can see that it is taking so much time right now. You can check the simulation time down below, and it is not finished yet. Okay, now let's see. Now it is almost done. Not yet clearly. Okay, it is it is done. Okay, now it is done. Everything is finished and we can end simulation in here, and we have filtered our noisy signal, this one to this one. We have changed its values. As you can see, they are not the same, and now we were going to go back to MATLAB and see if our filter worked correctly or not. Now we will do verification of our FIR bandpass filter. But to do that, first we need to open our filter signal txt file and read data from it. And it's a very easy process. Let me show you. First we were going to create a file path. Then we were going to use FIR open function to open our txt file. Then we were going to use text scan to scan all of its values. But we need to use this command to read hexadecimal values. Then I have created an hex values parameter, and this is it. This is all you need to do. And after that, I need to change those single procession hexadecimal values to numbers. And to do that, I have used hex single to number function. This is a special function and it is not in MATLAB, and I will going to share this function with you. And after that, I have just created a decimal values parameter, and this is it. This is my filter signal. And lastly, I will going to plot my filter signal with my original signal, and let's see the differences. Now, orange one is my original signal and blue one is my filter signal. And you can say that, look, there is something strange is happening at the beginning, and this is completely normal because at the 0 point all of my tabs are empty and they are going to fill it with the time. So this means all of my data into the 180 point is invalid. But after the 180 points, all of my data is correct. And you can also say that my filter signal is shifted. But this is also normal because filters adds delays. In this example, because of my 180 tap bandpass filter, my filter signal is shifted 90 points towards the time. And this is it. This is all. Thank you for listening to me.